Hey, Vlad here, devinside.com. Welcome to another video. 2 videos ago, we realized that pretty much every method on sets was implementing recursion in one way or the other to traverse the entire collection. And after realizing that, we implemented for each, which centralizes recursion in one place, and basically every method was calling for each. And today, we're going to add yet another one called fold, which is a bit more concise than for each. It is so concise that even for each we'll call fold. So prepare to meet the father of all recursive traversals, or maybe it's the mother. As always, we're in the Ubuntu virtual machine and we have Sublime on the top and we have our terminal at the bottom, which already runs SPT in our Homegrown Collections folder, and we're just going to run the test. And this is exactly where we left off. In fact, in the previous video, we implement map and flat map, and we started to work on generics. And you might have been hoping that this video would be about generics, but I want to keep it simple and progress with generics basically as slowly as possible. But no worries, we're going to get there because generics are a very, very important topic. All right, so I realized that we made a few, not really mistakes, but I've forgotten to improve a few things. For instance, the hashcode method, it is still not using for each. So we're going to improve a few things before we actually get started with the video. So I'm going to have braces around hashcode like this. Okay, I'm going to comment everything out. And I'm going to implement it with for each, right? So we're going to start with the result of 41, and in the end, we're going to return the result. And over here, we're going to say for each, as we are always doing, for each with a function, the txt current element. And we're just going to say result equals result plus current dot hashcode. There we go. And that should already be enough, unless I made a typo somewhere. It's kind of good to have tests, so now we know that we did not cause any regression. Okay, so let's remove that. All right, so now we have our hash code. And another tiny thing that I realized was that in the test for things like intersection, let me find it real quick. Here, intersection, we're still using this sort of silly way of writing the test. So we're doing empty set, intersection was an empty set, and if we're asking if we're going to ask it if it contains the random string, it should say false. Now this is an okay-ish test, but by now we have equality, so we might as well do something like this. We can say set.empty intersection with set.empty should be set.empty. Which is a bit better because our equality goes for subset and subset of both of each other, subset of each other, and therefore it's a better test. So I can just copy that and we'll go to difference, and I believe difference is doing the same thing over here, right? So instead of doing that, we're just going to do that. Okay, now so everything is cleaned up, and now we can actually start with the video. So the goal of the video is to implement a function called fold, which is going to do something very, very similar to for each. Let's go to the top. And by the way, a bit later I'm going to explain why it's actually called fold. So if you look at our functions, like for example apply or add or remove, all of them, they have the similar structure, right? So they have result, and they call for each with some function, and then they return the result. Same thing over here, result, same thing over here, result. Basically every method, even hashcode that we just wrote was following this pattern. If you look closely at this, and so what I'm going to do is I'm going to copy apply, and I'm going to call it apply, I don't know, apply to or something. And it can't be an override anymore because what I'm going to do is I'm going to copy it over here, and this is going to be our apply. This is going to be the one that I'm going to modify a little bit, and then you can see how close is it to the previous one. Okay. So what we need to realize that a little bit more is happening here. So this is highly imperative code, meaning that we have some mutation over here, right? And because we have some mutation, this variable, it can represent many things, right? So it's called result, but in the beginning it has a different meaning. In the end it has a different meaning, and during this for each it also has a different meaning. So if you look at it closely, and then in the beginning, we always give some sort of initial value, right? So for applies, it's a boolean. For add, it's a non-empty set. For remove, it's an empty set. For union is that, and so on and so on and so on. Okay, so we always start our computation with some sort of seed, some sort of initial value, and in fact, this is how it's called. So we're gonna have a seed which is going to be false. So in the beginning, our result is actually seed, right? And I'm going to constantly keep repeating, running the test so that we see that I'm not actually breaking anything. Okay. So the next thing that we're going to realize that while we're inside, as long as we're inside of this for each method, what we're doing here is we're basically accumulating some result. So in fact, over here, we're not changing the result, we're changing some sort of accumulation. So this is actually some sort of accumulator, right? And only in the very end, we're gonna have a val of result, and we're just gonna assign the accumulator to that, and only then we're gonna return the result. So in fact, in the beginning we had just result, but now we see that there are actually three things that are happening there, right? So there's a seed value, then there's some sort of accumulation of the result value, and then by the end, the accumulator, whatever has been accumulated, becomes the result, and the result is just being returned. One interesting thing to notice is that the result, or the seed and the accumulator and the result, because they were like in the beginning they were one thing, they all have one type. It doesn't have to be a boolean. It can be, sometimes it can be a boolean, sometimes it can be a set. For example, in add, it is a set. In fact, let's rewrite real quick add as well. So if we have a seed, which in this case is a set, right? This one. Okay, so this is our seed. I'm gonna put it over here, and now this is an accumulation. Basically, everywhere where it says result, I'm gonna type in ACC, and over here we're gonna have result equals ACC, and it should be exactly the same code, right? So I just wanted to point out that the seed, it doesn't have to be a boolean, just in this case it's a boolean, in this case it is a set. So what we want to do now is we want to implement a function called fold, and once we call fold, it should look like this. So I'm gonna comment this out, right? So it should basically record in the type system everything that I have written here. So it's gonna look like this. We're just gonna call it fold, right? And as the first parameter, it's going to get the seed, and it's just in this case the seed is false, so I'm going to do this equals false, right? As the second parameter, it's going to get basically this function that takes the accumulator, right, and it takes the current value, which is this, right, and it produces some sort of result, right? So this is going to be I'm going to call it function, right? And this function is going to be of type, and we're going to start with a non-parameterized function. So we're going to start with a function that takes the boolean, right? This is the accumulator, the boolean, and it also takes the current element, right, which is of type element, right? And it produces, in this case, a boolean. Now over here, I'm calling fold, I'm not declaring fold, right? So I just typed out the type so that you understand it a little bit better, right? So over here we need to pass in actually the implementation, right? So we're gonna, instead of this, actually, you know what, I'm gonna duplicate this, I'm gonna comment this out just so that you see the type. Okay, so over here we're gonna say function equals, right? And in this case it takes the accumulator and it takes the current element, right? And now an arrow to the right, right, because this is the implementation of this function, right? And now what we can do is we can copy that. Can just literally copy that, paste it over here, right? The input is still in scope. It is over there, right? And this is it. Now it is a common thing to write fold as a current function, right? So it is a very common thing to write it in such a way that these parameters are separated like this. And in the second parameter, then you cannot use a named arguments, right? So it's gonna look like this. And usually also it's sort of like a convention to write the second one with the curly braces instead of the parentheses like this, right? And because of that, you can sort of fold it to fold it, no pun intended. You can just put it on the next line like this. In fact, it's not like this. It's usually it's like that, and after the arrow you put it like this. So now you sort of see now it's sort of starting to look like for each again, right? It's just that there's additional accumulation there. So this whole thing is basically going to be the result, right? So if I do that, now this is going to be the result, because fold, sorry, I'm not sure what happened here. So what fold will produce is this result, right? So, and then in the end, we're going to return the result. Now, this is a bit more explicit than before. In fact, I'm going to remove it in just a second. I just want you to see the similarity. So we have exactly the same thing. So we have some sort of seed, right? Which is, in this case, is false. And then we have this function that takes the accumulator. So in the beginning, what fold will do is it will do literally the same thing, right? It will say, okay, the initial value for the accumulator is going to be the seed, right? And then it's just gonna walk through the entire collection. We're gonna implement it just in a second, right? And then it will apply basically this function, right, to the accumulator and to the element that it is currently traversing. It's very, very similar to for each. And I'm going to show it to you in a second. And then by the end, whatever is being accumulated is being assigned to the result, and the result is being returned. Now I'm going to remove this like that, and I'm going to remove that. Okay, so now if I try to compile, it's obviously not going to compile because we don't have the function called fold. So I'm going to comment fold out, and I'm going to do that, right? So that we go back into the working code. Okay, so in order to implement fold, we're actually going to look at for each, and we're going to see how for each it's doing. What I'm going to do now is I want to bring it sort of closer to this function. So I'm going to go down and I'm going to find for each. Where is it? For each. Okay, it's over here. So for now, I'm going to cut it out. I'm just going to bring it closer so that hopefully you can see the entire code. Probably not, because I don't have much space that I'm working here with. Okay, all right, so okay, that's the wrong position. Hold up, it should be over here, right? So this is for each. So what I'm going to do is I'm going to implement fold just above for each, so that you see how it's being called, and also that you see how it relates to for each. Now before we get started, we're going to do a few things. So let's look at for each, for example. What for each is doing, it says, okay, in case this is a non-empty set, then I'm just going to rip out the element, and I'm going to rip out the other elements, and then I'm going to apply the function to the first element, and then I'm just going to go through all the other elements and apply the same function to them, right? Now, there are quite a few things happening here. So first of all, the return type is a unit. Therefore, we don't have to have an else case, right? Well, what is going to happen in the else case? So in the else case, technically what is happening is that the unit is returned, right? So this would be, if I still compile the code, it's going to do exactly the same thing, right? It's just right now it's a little bit more explicit. So the first thing that we're going to do is we're actually going to flip this expression. So we're going to say if is empty, then we're going to produce this unit. Otherwise, we're going to produce this other thing, right? So let me comment this out. Right? This is just a refactoring, exactly the same code. So before we had if not empty, just do this block. Now just a bit more explicit. If it's empty, then just return unit. Otherwise, do that, right? And the other thing that I'm going to improve is that, not improve, but just make it a bit more explicit, is the same thing that I did 2 videos ago. So what is happening here? I just want to point this out, that we're calculating the result of what's going to happen if you apply the element to this function. So this is going to be the, I'm going to call it element result, right? Which gets thrown out, right? It's not used anywhere here, right? And this is going to be called, I'm just going to call it result, but this is technically like other elements result, right? And this is what is being returned. Now in this case, result is still a unit, right? So the type of this is still a unit, and the same over here, the type of this is a unit. Right, but when we're going to implement fold, we're not going to have a unit. We're actually going to have something that is very, very useful. In the first case, it's going to be a boolean, right? So I did all of this just to show you how very similar fold is. In fact, maybe I should copy for each. No, I'm not going to copy for each. Or maybe I will. Yeah, I'm going to copy for each. I'm going to copy for each. I'm going to put it over here, right? And I'm going to call it fold, right? Now, it is going to be parameterized with result. Like in the beginning, I thought maybe we should do it like only with the boolean first, but in fact, there's no reason to do that. Okay, so it's going to be called fold, and as you can see here, it's a current function. So it needs, as the first parameter, it needs a seed, right? So it's going to be a first parameter seed of type result, right? So again, I wanted to use it as a boolean first, but let's do result. Okay, so and the second parameter is a function, but it doesn't only take the element, it also takes this accumulating result, right? So we need to add a parameter over here, and it is of type result, right? So we can't give like 3 different names to the result type, right? Because we know that the result was acting as a seed and as accumulator and as a result type, but we have to give it only one name. So I chose to give it the result as a name, right? Okay, it is basically a very, very mechanical transformation, right? So if it's empty, we're just going to return the seed, right? Our seed can also be unit, right? So we're just going to return the seed. Otherwise, we're going to do the same stuff as over here, but this is not going to be unit. This is going to be result, right? So we're going to call the function, but we need to also carry not only the element, but also the result. And in the beginning, we don't have anything except for the seed, right? So remember, like this is basically what I wrote over here in this line is what is happening over here. The initial accumulation is the seed, right? So we call a function with the seed and with the element, and this is how we're getting the element result. And then we're going to do the same thing for the element. Instead of calling for each, we're going to call fold, and as the first parameter, we're going to give it current result. Right, it's that thing that we just created. Sorry, this one. And that's it. This is the entire fold, except for the fact that I forget to also mention that we're returning the result. This should be it. And this is fold. Now, as you can see, it looks literally exactly like for each, right? So it turns out that we can actually sort of as a proof that it's sort of the same thing. If you implement for each in terms of fold, then we have all of these tests that we have written for all of our methods sort of for free, right? So let's do that. So instead of all of this, right? Instead of all of this, let's just call fold, right? And the initial seed is going to be just a unit, right? And over here, we're going to have a function which takes the accumulation and the current element, right? And what will it do? Well, it will just apply the function to the current element. Let's see. Everything is still green. In fact, in this case, we're actually not even using the accumulator, so we can just do that, right? How cool is this? Let's remove that. Okay. Let's go back to our initial example was the apply, remember? So we should be able just to do that, and actually I can comment this out. We don't need this anymore, right? And our test is still green. How awesome is that? So I'm going to remove this. By the way, you know that this is a seed, so I'm going to do just that, right? Okay, like this. And I'm also going to remove the old apply function. Right? We don't really need it. By the way, I forgot to mention this. Our code is going to be more concise, right? So in the beginning, I forgot to show you this, but in the beginning we had around like 200 lines of code. Let's see how much we have now. Yeah, right now we actually have even a bit more because we added a function, or we added fold. But by the end of this video, we should have like, I don't know, maybe like around 150 lines, because everything with fold is going to get shorter. In fact, let me show you if I scroll up. This apply function. Let's see if we can do something with there. No, I think in this case we can't. Actually, we can. Like maybe it's gonna look a bit more weird. Like, look, in this function we're using the accumulator only once, and we're using the this parameter only once, and we know already from the video from a long time ago that if we're using the parameters only once and in the same order as they are declared over here, then we actually don't have to give them names, right? So we can just comment this out, and now ACC doesn't exist and current doesn't exist, so we can just use underscores, underscore here, underscore here. Now, you could argue that this is now less readable, but if you're actually used to using folds, then this will be, you know, sort of clear, right? So what we can do now is I can remove the end of this line, and because the line is so short now, I can replace these parentheses, sorry, the curly braces with the regular parentheses, and I can remove the space. I can press Ctrl J, which will join lines like this, right? So this entire function now is just a one-liner, right? So it's just one call to fold. This is what usually happens with functional code. It just gets more and more concise, and also now because it's one expression, you also don't need the curly braces. In fact, the entire fold is still one expression, right? Now, before we continue replacing basically every call was fold, right? Because remember, most of the methods still call for each, and then for each calls fold. Now, there is no need for that. We want to, you know, flatten this hierarchy a little bit. So what we want to do is we want to go through every method and just call fold, and we don't even have to explicitly test fold, because basically all of our tasks are going through these other methods and test them for free, right? So before we continue, let me point a few things about fold. And the thing that I want to point out is premature optimization. Now, beginners and actually even experienced developers, they sometimes have this tendency to be like very smart. And because of that, the first time they write their code, they want to write it as perfect as possible. But in fact, it just doesn't happen. You know, after like, I don't know, 10 years of experience, you know, I hope much sooner, you will realize that even though you have so much experience, you can't actually, you know, very, very rarely you can write code perfectly the first time you write it. It's an iterative process. It's the same as, you know, writing an essay in the, you know, in the English class or whatever, right? So you write it out, it's some garbage, you throw it out, you try it again. It's an iterative process. Okay, so what beginners tend to do is they tend to optimize their code prematurely. So for example, in the very beginning, we had like these, you know, 8 or 9 functions, and they were all doing recursion. Now remember that recursion can explode if the tail calls are not eliminated, right? So if not every recursive function can eliminate the tail calls, because the call might happen not in the tail position, and then the compiler cannot help you out. So we could have started, you know, adding the annotation everywhere and making sure that it's at least tail recursive. which by the way, it's technically not an optimization. It's called tail call elimination, but still, it's same idea, right? So we could have started doing that and basically waste time, but instead we went to for each, and then we had recursion only in one place. But even there, we sort of didn't really check if it was tail recursive or not. In this case, I know that we're not going to have a higher abstraction than fold. Like this is basically the last one. Therefore, we're gonna try and see if it's tail recursive, and it should be. It's just that if I add this annotation right now, Scala annotation dot tailrec, and if you don't know what this is, rewatch the video number 7 or 9, I'm not sure. Okay, so as of right now, it says could not optimize tailrec annotation method fold. It contains a recursive call not in the tail position. Now the thing is that because I made it so explicit, after it goes to this recursion and comes back, we have this result, and the compiler is sort of not smart enough to figure out that we're actually not really using this result. We're just returning it. So if I remove that, right, and just straight return this last statement, which is what's happening was regular Scala function, then what's happening here? What did that? Right, then the compiler will actually be able to eliminate the tail calls, and everything is fine. And now you know that this is a tail recursive function. In fact, if I remove that to make it a little bit shorter, right, the entire fold is tiny enough so that I can just inline this. Remember, the substitution model of computation allows me just to do that because there are no side effects, and now we actually don't even need that, right? So the entire implementation of fold is like this. Now, one last thing that we're going to do before I'm going to go through all the methods and implement them in terms of fold is I'm going to re-implement fold with a while loop, because I know that some of you might not be used to this highly functional code, because like this is not the easiest thing to read, maybe, if you're not used to it. So just for educational purposes, I'm going to implement it with a while loop. I'm not going to commit it though, so once I'm gonna finish implementing, just pause the video, look at both of them and decide which one you like more. All right, so I'm gonna comment this out, and actually this one as well. So I'm gonna copy this first line. This is the signature, right? So it has to stay the same. Okay, comment it in like this. Now, because we're gonna use a while loop, we're actually gonna end up needing braces because we need this code. So what we're gonna do is we're gonna have an accumulation, which is the seed as in the very beginning, right? And then we're gonna have a current set, right? And the current set in the beginning is gonna be this, right? And then in the end of this computation, we have to move forward two things. We have to move forward this result, and we have to move forward this element, right? So we need two vars for that, right? This is what we have them, right? By the end, we're gonna have the same thing as always. We're gonna have result equals ACC, and we're just gonna return result, right? So now between these two lines, there will be a loop, right? There will be a loop that will modify the ACC, and it will also modify the current, right? So the loop is gonna look like this. I'm gonna say while current non-empty, we're gonna do something, and what we're gonna do is going to be the same as over here, right? So we need to deconstruct this thing. In fact, I believe in the next video we're gonna improve this a little bit, because I ended up copy pasting this all the time. Now, very careful here. We're not gonna ask if this is an instance of non-empty element. We're gonna ask if the current is an instance of non-empty element, right? Because with every iteration of the while loop, we're gonna strip off sort of one element, right? And we're gonna work only sort of with the tail of the set. So this tail of the set is gonna become current. So in the next iteration, we're gonna ask if that is a non-empty set. Okay. So what we're gonna do here is we're gonna modify the accumulator, right? We have two variables, so we have to modify them. Well, we're just gonna call the function with whatever currently is in the accumulator and with the element, right? And then we're gonna say current equals, well, it's just the other elements, right? So this is basically the moving forward with the list, right? So we're sort of forgetting the element. The function has already been applied to the element. Then we're just gonna go to other elements, right? And this is basically it. So I believe it should work exactly the same. Yeah, it works exactly the same. Okay, so I'm gonna scroll up and let's see if you can see both in one screen. Okay, I'm gonna press F11 just so that you see both. So now you can actually pause the video and look at this and compare them. But this is basically the same code, except for over here, you can't say maybe you can. I'm not sure if you can. Hold up. Can you do that? Can we do that? So we can say if current is empty, then don't do anything. Otherwise, do this while loop. We probably don't even need the braces. maybe it's gonna work. Okay, hold up, I need to comment out this other fold. Yeah, it works. Okay, so now I'm gonna comment it in again, maximize. Okay, so now it's even more close to this, right? So if it's empty, the seed, and otherwise we're gonna do this iteration. Remember, so over here we had recursion to help out with that. Over here we have this. All right, so I hope that you find this implementation a bit neater, which happens very often with functional code. So I'm going to remove that again, right? And let me just, I forgot to minimize Sublime. There we go. Okay, so what I'm going to do is I'm going to move for each down again to all the other high order functions like map and so on. Where is it? Where was it? Over here, right? There we go. Remember, even map and flat map, they were implemented in terms of for each, but we're just going to go top to bottom and just implement all of them. Okay, let's go back. Okay, so let's see. So we have apply. It's happening in terms of fold. Now we have the add. It's happening in terms of for each. So let's start with that. So let's do fold. It's a very mechanical transformation, right? So our seed is this, like this. Just copy it in there. Then we have over here the function which takes the ACC and the current element, right? And we're just gonna do that. Put that over here, except for this, we don't need that. And over here, we always need to return something, right? So we cannot just ignore the other branch, right? So we have to say otherwise, just leave the accumulation alone, right? So in fact, like as you can see, I didn't even think about what I was doing. I just like mechanically transformed this thing, right? And I just prefer to flip that because like the more you can survive without negation, the better, right? So if I flip that like this, then I can just flip these, and it will work exactly the same. Okay, like that. All right, so let's comment out this. Right, and because again now it's just one expression, you know, the expression is a bit longer, but still it's one expression. We even don't need the curly braces. And remember the cool thing about remove and add, that they look exactly the same, but their seed is different. See, the seed for the add is a non-empty set, and the seed for remove is an empty set, right? So I can just basically copy that entire thing, put it over here, for example, right? And I can just say, okay, my seed is just different, like that. And if I remove this and I remove the curly braces, I believe the Scala reform can figure out the whole indentation. It's just going to fix all of that for me. There we go. Okay, so as you can see, it's literally the same code. In fact, I can do this and press Ctrl D and it will mark it. It's exactly the same code. Like in fact, like you could actually, you know, put it in the private def if you wanted to. Maybe you should do this as an exercise. All right, let's just keep going. Okay, so we have a union. So as always, it's a fold. It starts with that, and then it has a function with ACC and current. And by the way, if if you're sort of falling asleep and while doing mechanical transformations like this, ACC and current, they have different types. So the compiler is going to warn you if you mix them. If you confuse them, right? So over here, what are we doing? We're just doing the result at current, which in this case is just ACC.add current. Now there's also a different syntax for this. First of all, let me just remove that like this, like that, and because we have our test, it's just going to tell me if we're still good. Yeah, we're still good. Okay, now there's an infix notation for Scala methods, as you already know. You can just do that, and because we can do that, look, it's the same pattern. We're using the accumulator only once, and we're using the current only once. So what you can do is, as always, you can just do that. Use one underscore over here, the other one underscore over here, and you're pretty much done, except for the fact that we're going to use the regular parentheses like that, and Control J, just remove this parenthesis, and it said, look how tiny and cute it is. The union is just fold, where we're adding everything to that. This is awesome. Like I love this. All right, so the next one is intersection. As always, comment this out. It's gonna fold that. What is our seed? Our seed is the empty element, like that. Over here, we have a function, takes the accumulator, takes the current result. Okay, there we go. And what is happening over there? Well, we're just gonna copy these, put them over here, comment them in, remove this mutation, add the other case. Otherwise, it's just the accumulation is gonna be just left alone. Let's remove that. Let's remove the curly braces. And let's allow Scala reform to fix the indentation. And what's up? Oh, result is not there. It should be ACC. There we go. Now remember that intersection and difference, they're pretty much the same thing. It's just that they're flipped, right? They're flipped, so I can just copy that. And I believe that I'm right. I can copy that over here, and I can just flip these, right? Because remember, intersection is basically an and the difference is and not. And our test taught me that we're still good, right? So it's exactly the same code, just flipped, right? Yeah, okay, anyway, it's just flipped. All right, so is subset of is the next one. And as always, comment this out. Go down like this, fold, our seed is true. I'm gonna have a function over here. Same as always, ACC, current, arrow to the right. What is happening over there? Only this thing. It's just that the result is actually ACC, and that should be fine. Yep, it's fine. So let's remove that. Let's remove that. Let's remove that. And over here we see ACC and current is being used only once. So we can do underscore here, to the regular parenthesis here, to the regular parenthesis here, remove that. Okay, Control J, Control J. Let's see if a Scala reform can remove those. Yeah, okay, perfect. All right, what is the next one? Next one is hash code. Same as always, comment it out, fold. The seed is 41. By the way, it's probably not ideal for the hash code to always have like this constant value for something even though it's empty. At least it's not zero. All right, so we have ACC, current, arrow to the right, and over here we just have result plus current hash code, right? And result is just called ACC, so that should be fine, right? And over here we're using it only once, ACC, current code hash code. Very mechanical. One parenthesis. Sublime just added the other one. Come on, remove it. Whoa, what's up? Okay, what's happening is that my wireless keyboard died. I knew that one day it would happen during recording. It's just a matter of time. All right, so what we're doing, we're removing this parenthesis, replacing it with this one, pressing Control J a few times, and removing that. Everything is so tiny, so cute. It's one of the many reasons why people like functional programming. It's not the only one though. All right, so let's see. Still fine. Okay, this one. Let's see if I can write it. No, I can't over this. Okay, so let's do fold again. The seed is 0. Okay, so we have the accumulator and we have the current. Let me remove the cursor. Let me go to the right like this. Okay, so all we're doing is we're adding 1 to the accumulator. Remember, because we're just, basically if the element is there, we just add a 1, right? And by the way, we ignore the current, so we can do this, okay? And by the way, this is also another thing for you to know, like if you're not using one of the arguments, you can't use this short notation. Like this, remove that. All right, okay, so it's still fine. What else is there? No. Basically, we're looking for things that use for each. Okay, so there's only map left. Map is a higher order function, but still, it's gonna look pretty much the same, very mechanical. So we're gonna do fold over here. The seed is empty result, like that. Let's have the function as always, accumulator, current, arrow to the right, over here. So we're just gonna copy that. That's just going to be called ACC. That should already be enough. Yeah, there we go. Like that, and like that. And again, we're using the accumulator only once, so there's going to be an underscore, and we're using it only once over here, so it's going to be like this. Maybe it's going to be a little bit prettier if we use the infix notation, like that. So if you don't see this transformation, like how it became this notation, then I'm sure that the syntax is a bit confusing. This is also, Scala is sort of known as a complicated language because one of the reasons for that is that it has like so much syntactic sugar. So if a beginner looks at this, it is basically unreadable. But if you see like where this is coming from and you're sort of used to this, which, you know, the entire Scala community obviously got used to, then it just makes sense. It just does. It just, like, I look at it and I know exactly what it's doing. But for you as a beginner, like, maybe, you know, spend a little bit of time with this. I hope that the way I'm showing this, like, you know, those mechanical transformations, because they're so mechanical, you're gonna understand them better. But I'm pretty sure that even if you understand it now, you're still gonna forget it unless you play with it. So as always, you know, clone this thing, play with it, change things around, change the types, change, you know, the orders, see what's gonna explode. You know, we have the test, add some, you know, some of your own tests. You can also submit pull requests. I'll accept, you know, all of them unless unless you break some tests. Obviously, don't break tests. And also, we haven't really started looking at our code coverage. But basically, whenever you're submitting pull requests, just at least make sure that the code coverage doesn't go down. Okay. All right. So I believe we're done with this, and the last one is actually flat map. Now, flat map is a bit tricky, right? Because we're gonna have two folds in there, right? So over here we have 2 times the for each. So we're gonna end up having fold also 2 times. Okay. Let's still try, you know, to keep it like mechanical. So comment this out, and we're gonna have a fold over here, and our seed is going to be the empty result. Let's see if I can figure this out. Okay. Now, instead of ACC and current, we're gonna have outer ACC and outer current, right? The same as before. See, we had the outer current, right? Now, the first thing that was happening is that the function was applied to the outer current. Well, we still need to do that. The function is applied to outer current, right? Exactly as over here. And then for each was called, well, this means that we need to call fold, right? And the seed for this is going to be outer ACC. This is going to be the seed. It's just going to be passed over here, right? And now over here, we're going to have a function that will have inner ACC, and it's going to have inner current, right? And what it was doing is basically copy pastable, right? So we can just do that, paste it over here. It just said the result is actually that, and I believe, I'm not sure, but I think that's fine. I think that's exactly that. Yeah, that's exactly that. So I'm gonna comment this in just real quick so that you can pause the video and compare these 2 implementations. It's very mechanical. Look, for each is used in the same positions as fold. The function is applied to the same thing. It's just so we're carrying this accumulator explicitly with us all the time. Okay, so let me throw this out, and let me make it a little bit more unreadable, with this fancy syntax that we so love. Okay, so first of all, let's do the infix notation like that. Technically, we don't have to do this, but actually, let me show you. So if we don't do this, right? So if we just use an underscore over here, and we use an underscore over here, right, and just throw these out like that, then I believe that this is more readable than this, and that's why I'm always doing this, right? So let's just throw this out. Let's go over here, curly brace, parenthesis, and let's do that. Let's do that. And there we go. This is our fold. So technically we could call it ACC now. Let's actually do this. Why not? And this could be the current now. Right. So now there's no need to explicitly call it outer. Technically, even before, it was not really necessary because of nesting of the scopes and the shadowing. But still, look, the entire flat map is now so tiny, cute. Okay. So right now we're already at 147 lines, and we're actually gonna get it even more down because the very last one that we have is apply. Remember, apply is also using for each, but it's not using for each on our sets. It is using for each on the Scala sequence, right? Because other elements, remember this var args thing, is just a sequence. So it turns out that Scala collections and sequences, they also have folds. I mean, I clearly did not invent this stuff. Okay, so the only difference is that because it's a sequence, it has an order, and therefore it doesn't only have fold, it actually has also fold left and fold right. Now the difference between fold left and fold right is the following: the traversal of the collection is always left to the right, but if we're doing fold left, what we do is we're taking the first element, we apply the function to it. Right, that's the first thing that's happening, and then we keep going, and we keep doing that. We keep applying the function. So in the very beginning, we apply the function to the element and to the seed, which became the accumulator. In the second element, we apply the function to the to the second element and to whatever is being accumulated, right, and so on and so on and so on. Whereas with fold right, By the way, we're going to have a completely separate video for fold right once we're going to start talking about streams, because over there it's very, very important. What fold right is doing is it just does the whole recursion. It goes until the very, 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 very end of the set. I mean, set doesn't have an order, right? So therefore fold right doesn't make sense, but a sequence does have an order. So it goes like from left to right, but it doesn't apply the function. It only applies the function once it comes back. And this is also why one of the reasons why these methods are called fold, because you can imagine a piece of paper, like a tiny piece of paper, like a line, right? And you have your elements in there. And when you start folding this piece of paper, if you didn't fold left, then while you're folding, you're applying the function. And if you didn't fold right, is when you're folding the whole thing, and when you're unfolding back, only then you apply the function, right? And they have two very important properties that we're going to discuss later when we're going to have the video about streams. For now, we can basically pretty much call fold left instead of fold, and it's going to work exactly the same, right? So it's going to be a mechanical transformation again. I'm just going to comment this out, right? I'm going to go over here, and I'm going to say other elements, fold left, right? So first of all, we're not just calling fold on this, we're calling fold left on other elements, because this is what we're walking through, right? And the same as before, it has a seed, and our seed in this case is this, right? So it's an empty set with the first element added, right? And over here we have, as always, we have our ACC, and we have current like this, and we're just gonna copy that, paste this over here, and you know that this is we know that this is ACC, right? We already have tasks for this, right? So it's doing exactly the same thing. Okay. In fact, in our case, I'm not sure if I can do. I'm just gonna try this. I believe if I do fold right, and again we're gonna have separate videos for fold right, then I believe these are swapped. I believe this is now current and this is ACC. I believe, I'm not sure. Yeah, so fold right, like in this case, it doesn't matter if you use fold left or fold right, but they actually have very different properties, right? And again, we're gonna have a very dedicated video for fold right. It's very, very important to know it. For now, just completely ignore that it exists. I'm gonna revert that to fold left, and as always, because we're using it only once, we can do that trick over here. This is gonna become an underscore. This is gonna become an underscore. All of this is gonna become an opening brace. And Sublime just does that for me. Curly brace is going to be gone. I'm going to have this over here. Remove that. Now we even don't need the curly braces. All right, and we ended out with only 140 lines of code. And if you look at the beginning of the video, actually, if you look at the commit on GitHub, I'm not going to do this now, but you'll see that we started with 200 lines of code. And now we added a fold, right, which is like, I don't know, 10 lines of code or something. So we're like 210, and we went down to 140, right? So this is like around, what, like 30% or something that we saved in terms of lines of code. Now you could argue that the code got like a little bit less readable, but trust me, it's only because you're not used to it. It's just not familiar. It's actually not less readable. All right. Okay, so let me see what we have here. That's fine. Yeah, so I believe we have everything we want. So what I also planned for this video is the first thing that I'm going to do is I'm going to commit that, and then I'm going to show you a few other things about fold in the Scala collection. I hope this video is not going to get longer than an hour. All right, so let's get out of RSBT. Let's do git status. Okay, we're only changing these two files. Okay, as always, you know that I prefer to do this, even though this is not necessary. Commit -am. Okay, so this is going to be video 5, I believe. And I'm just going to call it fold like this, video 5, fold, right? And I'm just going to push it right away. I'll load my key. All right, there we go. So if you see over here, if I refresh that, you can have video 5, fold, and you can look at that. And you can see exactly what changed. Pretty much everything changed. You see, like you see exactly how what we have rewritten. I don't know, like for example here, difference was like this, now it became like this. So basically, as always, we pretty much revamped the entire code base. Okay, so now what I want to do is I want to go back to SPT. And technically, we don't even need to be inside of this project. And what I'm going to do is I'm going to just create a main method, and I'm just going to show you a few things. Okay, so we're just going to have an object main extends app, and let's save this as main. Let's save it as playground.scala, right? And I'm going to call this playground. Okay, just because I can. Okay, as always, hello world, because otherwise we don't really know if it's actually working. All right, so there we go. We see our hello world, and I prefer also to do these hyphens so that's just a bit more explicit. So we're just gonna do hyphen times. Where's my times? Where's my times? There we go. All right, so now it's just a little bit more explicit when we print it out. Okay, so what I want to show you is that we're going to play with Scala collections. So what we're going to see is that a sequence, so let's say that we have a sequence of 1 and 2, right? So it also has fold left, right? So it has fold left, for example, 0, right? And what we're going to do is we're going to subtract. So we're going to subtract the first one from the second one, right? So the result of this is going to be I'm going to call it x1. It's going to be an integer, right? In fact, yeah, we're not going to do this because I just want to save some time. So we're just going to print it out, right? So we're going to print it out. It's just going to believe me that this is an integer, right? Int, like this. Okay, so what's happening is that the computation starts with a 0, right? And then it subtracts from the 0, it subtracts the 1, and then from whatever came out, which is -1, it also subtracts the 2, and then we have the -3. And now I'm doing this just to show you the default right. So if I swap that, I'm going to do fold right, and also I'm just going to say not just int, but I'm also going to say -3, and let's see what's going to come out over here with fold right. Now with fold right, it's going to happen -1, and I don't want to sort of spend time right now explaining this to you, because again we're going to have a very dedicated video to fold right. But basically you see that the order is different, right? So it goes through the whole recursion, and then on its way back it starts to subtract stuff. One of the reasons I'm doing this is to show you that it also has fold 1, 2, and fold looks like this, pretty much the same, right? So fold is doing the same thing as fold left. It doesn't always do the same thing as fold left. For some collection, it just makes more sense to do what fold right is doing. Now, the one thing that you need to know about fold is, hold up, like that. What is happening? Oh, it has to be here. There we go. All right. One thing that you need to know about fold, the difference between fold and fold left, is that if you look at the signature, fold is being forced to produce the same type as the type of the element of the collection, right? So we have a sequence of integers, right? And therefore, fold is forced to produce an integer, whereas fold left and fold right, as we have seen, it can produce whatever we want, right? The next thing that I'm going to show you is basically the same thing, but with a function called reduce. Now, reduce is a special version of fold over here, right? So the difference is that it doesn't need this seed element. So it's just going to take the first element as a seed, right? So if I do that, if I do that, if I do that, let's see what's going to come out. It's going to do 1, 1, 1, right? So it's not, it's obviously not the same because the 0 is missing, right? So it's going to do 1, 1, 1. Okay, and I believe, if I'm correct, that in Scala, reduce left and reduce right, they're all forced to produce an integer in this case, right? Because they're only working with the elements of the collection. Over here, we're basically saying, hey, this can be something else, right? This can be a string. The seed can be a string. So produce me a bunch of strings, right? With reduces, you can't, right? So fold, reduce left, and reduce right. They're forced to produce the element of the collection, right? So only ints can come out, whereas fold left and fold right, they can generate whatever you want. Now, what you should know is that if this is an empty collection, then it will actually explode, right? So if I have a sequence of empty, right, of ints, and I'm just going to say reduce, and then whatever I'm going to say there, it doesn't really matter. It's just going to explode because, you know, it wants to take the first element as a seed, right? So it explodes with unsupported operation exception, empty reduce left. Okay, so you just can't call it on an empty collection, which is why I really don't recommend using reduces. What I do recommend instead is using reduce option. So let me just copy that, put it over here, put it over here, over here, over here. I believe they're all called like this. All right, so what they're producing is sums in this case. Sum, and in case of the empty one, they're just going to produce a none. Right, so this is also a sum. This is also a sum. and the type of these ints is actually an option of int, right? In fact, we actually don't need this other line, other tab, so we can have something like this. Okay, and over here I'm also gonna add sequence.empty int reduce option, right? So this is an option of int, and it should be none, right? So it should be somewhere over here. It's none. All right. The very last thing that we're going to talk about is we're going to talk about option. One thing about that you need to know about option is that it can be viewed as a collection of one element. And therefore, it has also fold left and it has fold right, which work exactly the same way as over here. The problem is that it also has the method called fold, but it doesn't behave as fold on collection. Basically, what happened is that it has been misnamed, basically, right? So it's actually not a fold. So what we're going to do here is imagine that you have some option. Right, you have some option, and let's say that this was an option of int, right? And we don't really care what's inside. What matters is that the type is option, right? So how do you get? So what we want to have is we want to map it to a string, right? And but if you map it to a string, then we get an option of string, right? So if you do something like x.map, and then whatever is inside, just map it to string, right? So it's like this. But how do you actually get a string, right? So how do you open the option safely? Well, it turns out that, let's have it as a def, okay? What happens is that you can have x.map to a string, and then you can say .get or else, nothing to map or something like this, right? So this code should compile, and we're not actually printing it out, but maybe we should. Let's go and print line that, okay? Okay, so yeah, okay, I mean, it throws over here. So if this was a sum of, I don't know, 27, then we would see 27. But if this was a none, like this, right, then we should see nothing to map. We're going to talk about get or else a bit later once we're going to start talking about variants. But what you need to know is that there's a function defined on option. There's a method defined on option that basically does a combination of map and get or else. Unfortunately, they called it fold as well, right? So instead of this, right, I'm just going to comment this out, right? So over here you can say .fold, and then you have nothing to map over here, right? And you can map, basically you don't need to map, it's just a current function. And the second parameter is basically whatever the map was doing. So whatever the map was doing is just the in the second parameter list, and whatever the get or else was doing is over here. Now, so this is exactly the same code. So if it's none, then we're going to see nothing to map. Technically, it's nothing to fold. And if it's sum of some number, then we should see this number, right? So I'm just making this just to show you that even though it's called fold, it is actually not really related to fold. I mean, sure, you could sort of guess somehow that it's, yeah, but anyway, it's not fold, and a bunch of people in the Scala community are complaining about this, but you know, whatever. It's just like one of those things that you need to know. It's called fold, but it doesn't behave anything like this fold, okay? I believe that this is it, and yeah, one tiny thing that you need to know about fold is that sometimes it doesn't have such a good type inference, and we're gonna talk about this again once I'm gonna make the video about variants, because like this is, you know, the video about variants is gonna be a very exciting one, because this is where we're gonna see the true blend of functional programming and object-oriented programming, and we're gonna see that you know, this is not a very, you know, smooth and nice picture. All right. Okay, I believe this is it for this video, and I have no idea how it got so long again. Anyway, like it if you did, subscribe if you want to improve the developer inside you, and most importantly, take care.